picture the Milky Way. The whole thing, 100 billion stars, 400 billion if you count the dim ones, all spiralling in a flat disk, roughly 100,000 light-years across. A structure so vast that light, travelling at 299,792 kilometers per second, takes 100,000 years to cross from one edge to the other. You live inside it, inside one arm, in a suburb 26,000 light-years from the centre, on a pale blue dot that would fit into the galaxy's disk more than 6 trillion times over. Now picture 100 of those, end to end, a chain of Milky Ways stretching across the void. That is not the size of the largest galaxy ever discovered. That is merely where it begins, because there exists right now 3.5 billion light-years from where you are sitting, a structure so enormous that it has no parallel in anything you have been taught about how galaxies work. A structure produced by a single galaxy, a galaxy that is by every measurable standard completely ordinary, a black hole that, on paper, should be capable of nothing remarkable at all, and yet here it stands. The largest thing any galaxy in the known universe has ever made. What you are about to hear will not leave you the way it found you, because the story of the largest structure of galactic origin ever discovered is not a story about size. It is a story about time, about violence conducted at cosmic scales, about a young Dutch scientist who found the wrong thing at exactly the right moment, and about what the discovery means for every living thing that has ever existed on this or any other planet. Let's start with what we thought we knew. For most of human history, the Milky Way was the universe, not a part of it, the whole of it. When Galileo turned his telescope to the band of diffuse light arcing across the night sky in 1610, he saw it for what it was, not a smear of gas, not a river of myth, but a river of stars, so many that the individual points of light blurred together into a single pale brushstroke. He had no framework for what lay beyond. There was no beyond. The stars were the world, and the world was the Milky Way. It took more than 3 centuries to correct that misunderstanding. The instrument that finally did it was not a telescope pointed at the sky, but a calculation, a mathematical argument made by an astronomer named Henrietta Swan Leavitt, working at the Harvard College Observatory in the early 20th century. Leavitt was studying a class of pulsating stars called Cepheid variables, stars that brighten and dim on a precise, predictable schedule. What Leavitt discovered, and it is one of the most consequential discoveries in the history of science, made by a woman who was classified in the observatory's employment ledgers as a computer and paid 25 cents per hour for her work, was that a Cepheid variable's period of pulsation is directly related to its intrinsic luminosity. The slower it pulses, the brighter it truly is. This is the kind of finding that changes everything quietly. What Leavitt had discovered was a cosmic ruler. If you know how bright a star truly is, and you can measure how bright it appears in the sky, you can calculate exactly how far away it is. Distance, which had always been the most impenetrable problem in astronomy, suddenly had a key. Edwin Hubble used that key in 1924 to do something that shook the intellectual world to its foundations. He pointed the 100-inch Hooker telescope at the Andromeda Nebula, a fuzzy smear in the constellation Andromeda that had been debated for decades, and found Cepheid variables inside it. He measured their pulsation periods, he calculated the distance, and the answer that came back was not hundreds of light years, or thousands, or even hundreds of thousands. The answer was approximately 900,000 light years, a distance so far beyond the edge of the Milky Way that the Andromeda Nebula was not a nebula at all. It was a galaxy, a separate island universe as vast as our own, floating in a space that suddenly had no visible boundary. The universe, in a single observation, had expanded by a factor that defies intuition. We now know that the observable universe contains somewhere between 2 trillion and 2,400 billion galaxies. That number has been revised upwards 4 times since the year 2000 alone. Each time new technology has allowed us to peer further into the cosmic dark. Most of those galaxies are dwarfs, small, irregular, faint congregations of a few 100 million stars, huddled around larger neighbours like satellites around a planet. But some are not small at all. The Milky Way, with its estimated 200 to 400 billion stars arranged in a barred spiral disk, is not a modest galaxy. Our nearest major neighbour, the Andromeda Galaxy, M31 in the catalogue, spans approximately 152 0-Zen light-years and is believed to contain roughly 1 trillion stars. These are the galaxies that most people, when they imagine a galaxy, imagine grand spirals, sweeping arms of star formation, glowing cores, magnificent objects on any human scale. But they are not the largest. Not remotely deep in the Abell 2029 galaxy cluster, at a distance of approximately 1.07 billion light-years from Earth, sits an object called IC 1101. It is a supergiant elliptical galaxy, also classified as a CD galaxy, the kind that forms at the gravitational bottom of enormous galaxy clusters, cannibalizing its neighbours over billions of years, accreting their stars into an ever-expanding diffuse halo. IC 1101 has an isophotal diameter, the extent of its detectable light, of somewhere between 123,000 and 169,000 light-years, depending on which measurement technique you apply. Its mass is estimated at 100 trillion solar masses, 100 trillion suns. It dwarfs the Milky Way the way a city dwarfs a house. For years, IC 1101 held the informal title of the largest known galaxy. It featured in countless documentaries, countless articles, countless YouTube videos in which presenters struggled to find words adequate to the scale they were describing. And it deserves every superlative applied to it, as a stellar object, as a gravitational engine, as a testament to what billions of years of cosmic cannibalism can produce. But here is where the story begins to get strange, because when astronomers in the 21st century pointed a new generation of instruments at the sky, instruments tuned not to the light our eyes can see, but to radio waves, frequencies billions of times longer than visible light, they began to see something that the optical telescopes had missed entirely. Something that made IC 1101 look modest, something that suggested the question, what is the largest galaxy? Had an answer that nobody had been asking the right questions to find. The galaxies we thought we knew were, in a sense, only the part of the story we could see. The rest had been waiting in the dark, whispering in radio frequencies, for a receiver sophisticated enough to hear it. What those receivers found, what one young researcher stumbled across while hunting for something else entirely, is where this story really begins. There is a frequency of electromagnetic radiation that passes through you right now, as you watch this, without your body offering it the slightest resistance. It passes through walls, through cloud cover, through the ionosphere, through the entire thickness of a human torso, without interacting with a single atom in a way that any living nervous system could detect. Radio waves, they are not exotic. They are the same phenomenon that carries your mobile phone signal, your FM radio station, the Wi-Fi that connects your home. At human-made frequencies, they carry music and speech. At the frequencies produced by the astrophysical universe, they carry something far older and far stranger. When astronomers first began detecting radio waves from space in the 1930s and 1940s, Carl Jansky detected the first cosmic radio signal from the centre of the Milky Way in 1932, using an antenna he had built from wood and brass pipe on a rotating cart in a New Jersey field. They were confronted with the realization that the universe they could see with their eyes was only one layer of a much deeper structure. The universe they could hear with radio telescopes was different. It was populated by objects invisible to optical instruments, pulsars spinning 716 times per second, emitting lighthouse beams of radio energy, quasars, quasi-stellar objects, blazing from the early universe with luminosities 1 trillion times that of the Sun, and radio galaxies, galaxies from whose centres twin jets of plasma erupted, travelling at velocities approaching the speed of light, carving their way through the surrounding medium, and inflating enormous lobes of magnetised plasma that glowed in radio frequencies for tens and sometimes hundreds of millions of years. Radio galaxies were identified in the late 1940s. The first one recognised as such was Cygnus A, detected in 1939, and confirmed in 1951 to be a galaxy, not, as some had assumed, a collision between two galaxies, but a single elliptical galaxy blasting twin jets so powerful that they were visible at radio frequencies from 760 million light-years away. Cygnus A's radio lobes span roughly 500,000 light-years. At the time, that's at the physics behind these jets was not immediately understood, and in honesty, it is still not fully understood today, a point to which we will return, because it sits at the heart of everything this story is about. What is known as this. At the centre of most large galaxies sits a supermassive black hole. In the case of the Milky Way, that black hole is Sagittarius A, with a mass of approximately 4.15 million solar masses. In the case of more active galaxies, what astronomers call active galactic nuclei, or AGN. The black hole is not quiescent. It is accreting, consuming gas and dust that spirals in around it in a disk, superheated by tidal and frictional forces to temperatures of tens of millions of degrees. And in some configurations, when the magnetic field geometry and the accretion rate and a collection of other variables align in ways that physicists still argue about, in the footnotes of peer-reviewed papers, the black hole launches jets. These jets are not ordinary outflows of gas. They are collimated streams of relativistic plasma, a mixture of electrons, positrons, and in some models protons, laced with magnetic field lines, that travel at velocities between 10 and 99% of the speed of light. They erupt from the poles of the black hole's accretion disk, perpendicular to the plane of rotation, and they travel outward through the galaxy, then through the galaxy's halo, then through the circumgalactic medium, and then, in the case of the objects we are discussing, through intergalactic space itself for millions of light-years until they slam into the surrounding medium at their termination points and inflate those enormous, glowing, billowing lobes of radio-emitting plasma. The Phaneroff-Rayleigh classification system, developed by British radio astronomers Bernard Phaneroff and Julia Riley in 1974, divides radio galaxies into two broad categories. Phaneroff-Rayleigh Class 1 objects, the FRIs, are dimmer at their edges. Their jets fade as they travel outward. Phaneroff-Rayleigh Class 2 objects, the FRIs, are the opposite, brighter at their edges because their jets remain well collimated and powerful over enormous distances, producing sharply defined bright-edged lobes called hotspots, where the jet material terminates and piles up against the intergalactic medium. The largest structures are almost exclusively Fry objects. Their jets do not disperse. They punch through. For decades after their discovery, giant radio galaxies were considered rare curiosities, objects of academic interest, catalogued and measured and debated at conferences, but not thought to be common enough to matter much in the grand architecture of the universe. The number of known giant radio galaxies grew slowly, a few dozen, then a few hundred, then perhaps a few thousand, compiled across decades of painstaking work with various radio telescopes. Their typical sizes ranged from a few 100,000 light-years to, in exceptional cases, a few million light-years, impressive by galactic standards, but still operating within what felt like a comprehensible scale. Then LOFAR came online, and the entire population had to be reconsidered. LOFAR is not a telescope in the conventional sense. It has no dish, it has no moving parts of any kind. It is instead a distributed network of antenna fields. Tens of thousands of simple dipole antennas spread across the Netherlands, Germany, France, the United Kingdom, Sweden, Ireland, Latvia, Poland, Italy, and several other European nations, all connected by fibre optic cables to a central processing facility near Groningen in the Netherlands. The heart of the array occupies a radio-quiet nature reserve in the province of Drenthe, a place where mobile phones deliberately lose their signal, where the electromagnetic background is kept as clean as the physics will allow, where the antennas stand in their fields like fields of metal flowers, utterly motionless, listening to the universe at frequencies between 10 and 240 megahertz, radio frequencies that had been almost entirely unexplored at high resolution before LOFAR existed, what LOFAR can detect, and what previous radio telescopes largely could not. are the very faint, very extended, very low-frequency emissions that come from aging radio lobes. The old, cooled-down plasma of jets that fired millions or hundreds of millions of years ago. A conventional radio telescope pointed at these structures would see almost nothing. LOFAR's extraordinary sensitivity to extended, low-surface brightness emission, combined with its angular resolution of 6 arcseconds at 144 MHz, makes it capable of detecting these ghostly remnants that had been invisible to every previous instrument. The LOFAR 2-meter sky survey, LOTSES, begun in earnest around 2017, set out to map the northern sky at these frequencies with unprecedented sensitivity. Its primary science goals were varied and ambitious: the study of star formation in nearby galaxies, the measurement of AGN feedback on galaxy clusters, the detection of the cosmic web. But as the survey data accumulated and researchers began poring through the catalogues, something became apparent that nobody had fully anticipated. Giant radio galaxies were not rare. They were everywhere, not just dozens, not just hundreds. By the time the survey had covered roughly 15% of the northern sky, the LOTSS team had catalogued more than 10,000 giant radio galaxy systems. The population was 20 to 30 times larger than previous surveys had suggested. The largest structures in the universe, the largest things that individual galaxies had ever made, had been there all along, hiding in plain radio sight, too faint and too diffuse for earlier instruments to see. And somewhere in that flood of data, embedded in the reprocessed radio images of a sky survey that had not been specifically designed to find it, was a structure that would exceed everything that had come before. Not by a small margin, not by a factor that could be absorbed comfortably into existing models, by an amount that made the scientific teams stare at the image and wonder for a moment whether they had made a mistake. That image was found by a PhD student named Martin Oe, and the story of how he found it and what he did with it is one of the better human stories in recent astronomical history. In 2018, Martin Oe arrived at Leiden Observatory in the Netherlands as a doctoral student with a very specific problem he wanted to solve. The problem was not about giant radio galaxies. It was not about the largest structures in the universe. It was about something even more difficult to detect: the cosmic web itself. To understand why the cosmic web is such a hard target, you need to understand what it is. The universe on the very largest scales is not uniformly distributed. Matter, galaxies, gas, everything, is arranged in a vast three-dimensional network of filaments, sheets, and nodes, all woven together by gravity over 8 billion years of cosmic evolution. At the nodes of this web, where multiple filaments intersect, you find galaxy clusters, the densest congregations of matter in the universe, containing hundreds or thousands of galaxies in volumes that span tens of millions of light years. Along the filaments between those nodes, galaxies are strung like beads on threads, connected by flows of gas that feed them star-forming material from the intergalactic reservoir, and in the voids between the filaments, the cosmic emptiness that makes up most of the volume of the universe. There is almost nothing at all. The nodes of the cosmic web are detectable. Galaxy clusters light up in X-rays, in optical surveys, in the thermal imprint they leave on the cosmic microwave background via the Sunyaev-Zeldovich effect. But the filaments themselves, the threads that make up the web, are another matter. Gas in cosmic filaments, the so-called warm-hot intergalactic medium, or WM, is estimated to contain roughly 40 to 50% of all the ordinary matter in the universe. It is the reservoir from which galaxies draw their raw material, and it is, for all practical purposes, almost entirely invisible. The WIM is not invisible because it does not exist. It is invisible because it is vanishingly sparse. Densities measured in hundredths or thousandths of a proton per cubic meter, and because its temperature, in the range of 100,000 to 10 million Kelvin, is too cool to emit strongly in X-rays and too hot to emit in the ultraviolet, leaving it in a thermal twilight that almost no instrument can easily see. Detecting the WM directly has been described by cosmologists as one of the most technically challenging observational problems in contemporary astrophysics. As of the early 2020s, only a handful of confirmed direct detections existed, achieved through painstaking analysis of absorption features in the spectra of background quasars. Douai's doctoral project was aimed at a different approach. The idea was that giant radio galaxies, if they could be found in cosmic filaments, might interact with the surrounding WIM in a way that would leave detectable traces in the shape and pressure of their radio lobes. The plasma lobes of giant radio galaxies would, in effect, act as pressure gauges embedded in an otherwise invisible medium, the way a weather balloon measures the density of the atmosphere as it rises. Find the giants, map their lobes. Use the lobes to measure the filament. It was a clever idea, and it required OA to do something that most doctoral students do not spend much time on. He needed to find giant radio galaxies in large numbers across a substantial fraction of the sky. To do that, he needed to reprocess the LOTESS survey data in ways that would make faint, extended structures pop out of the noise. Standard data reduction pipelines are tuned to find compact sources, point-like objects that register as bright dots in the radio catalogue. They are not optimized for detecting the vast, surface brightness lobes that mark the termination points of giant jets. Getting those lobes to appear clearly in the images required a different calibration approach, a different choice of spatial filtering parameters, a different way of thinking about what the data was trying to show. OA spent months developing that approach. He wrote new analysis code, he reprocessed existing survey images, he tweaked parameters and ran the pipeline again, and he began to see structures that had simply not been visible before. Long, extended, double-lobed radio sources that had been washed out or overlooked in the standard processing. Over time, as he refined the technique, the number of detectable giant radio galaxies in the survey area climbed sharply. What had appeared to be a sparse population began to reveal itself as a dense one, but there was one structure in the data that was different from all the others, not just larger. Different in kind, most giant radio galaxy candidates show up in radio images as a pair of blobs. The two lobes, with a faint, compact radio source between them, corresponding to the active nucleus of the host galaxy. The standard identification process involves checking the separation between the lobes, measuring the angular size, confirming that the host galaxy is where it should be, and calculating the physical length based on the known redshift of the host. It is a routine procedure, and for 99% of the candidates, it produces a routine answer. For this one object, it did not. The two lobes appeared on 4 different spatial resolution scales in the LOES images, at 6, 20, 60, and 90 arcseconds of resolution, which meant the structure was both large enough and bright enough to register clearly on all of them. That alone was unusual. More unusual was the separation. When OAA and his colleagues measured it, and went to the catalogues to find the host galaxy and calculate the redshift, the number that came back was not a few million light-years. It was not consistent with anything in the known catalogue of giant radio galaxies, at a redshift of Z 0.2467, corresponding to a distance of 5 billion light-years. The angular separation of the two lobes projected onto a physical scale of at least 4.99 megaparsecs. 4.99 megaparsecs, that is 16.3 million light-years, expressed as a lower bound because the measurement captures only the component of the structure's length that is projected onto the plane of the sky. The true three-dimensional length of the structure is most certainly larger. For context, 3 million light-years is more than 163 times the diameter of the Milky Way. It is more than 10 times the size of any radio galaxy structure previously identified. The team looked at the image, they ran the identification again, they checked the host galaxy association, they verified the redshift, they looked at the image again. They were not looking at an ordinary giant radio galaxy, they were looking at something unprecedented, the largest structure of galactic origin ever identified in the observable universe. And the host galaxy responsible for it was not a colossus, was not a gravitational titan consuming 100 trillion solar masses of stars. It was a relatively ordinary elliptical galaxy with a stellar mass of 240 billion solar masses, comparable to a large but unremarkable galaxy in any survey. Its central supermassive black hole was estimated at between 220 and 560 million solar masses, with a best estimate of 390 million solar masses. A substantial black hole by human imagination, but modest by the standards of the radio galaxy population. Many radio galaxies are powered by black holes 10 or 20 times more massive. The team named the structure Alcyoneus, after the son of Ouranos, the primordial Greek god of the sky. In the mythology, Alcyoneus was the greatest of the giants, the one who could not be killed on his home soil, the one who fought against Heracles, and the Olympians for dominion over the cosmos. It was a name that fit, in more ways than one, because the scientific community's first response to the discovery was to ask a question that went to the heart of every model of radio galaxy formation. How? How does an ordinary galaxy, an ordinary black hole, produce a structure of this scale? What mechanism allows jets to keep firing, keep growing, keep extending through intergalactic space for the time required to inflate a pair of lobes 16 million light-years across? Every hypothesis the team reached for came back with the same verdict. Alcyoneus should not exist. This is what astronomers call a problem, and they had not encountered one quite like it before. Let us be precise about what the problem is, because it is not immediately obvious, and it is important. Giant radio galaxies, defined formally as radio galaxies whose lobe structures extend beyond 1 megaparsec, or approximately 26 million light-years, were already understood before Alcyoneus to present challenges for theoretical models. Their sheer scale implies that the jets powering them must remain stable and collimated over distances vastly exceeding the size of their host galaxy, travelling through an intergalactic medium that is not uniform, not quiescent, and not kind to long-lived structures. Anything that disrupts the jet, a passing galaxy, a fluctuation in the surrounding density, a perturbation in the accretion flow at the black hole, can redirect it, decelerate it, break it apart, keeping a jet pointed in exactly the same direction at sufficient power to continuously inflate a pair of radio lobes for tens of millions or hundreds of millions of years is a constraint that significantly limits the number of physical configurations that can produce a giant radio galaxy at all. Before Alcyoneus, the prevailing thinking in the field held that the most important parameters for producing very large radio galaxies were a very massive black hole capable of sustaining jet power at high levels over long durations, a very massive host galaxy, providing a deep gravitational potential well and a large reservoir of material to accrete, and a low-density environment, so the jets encountered minimal resistance as they expanded outward. These three factors were understood to work together. Larger black hole masses correlate with larger host galaxy masses, and both correlate with the environments in which very large elliptical galaxies typically reside. The logic was clean, testable, and well supported by the existing population of known giant radio galaxies. The biggest and most powerful radio structures known before LOFAR tended to be hosted by massive ellipticals sitting in relatively low-density filaments or group environments, powered by black holes of several billion solar masses. Alcyoneus broke every part of this model simultaneously. Its host galaxy's stellar mass of 240 billion solar masses places it below the median for giant radio galaxy hosts. Its black hole mass of approximately 390 million solar masses, which is the team's best estimate, though the uncertainty range extends from 220 million to 560 million, is not merely below the median. It is, as Oe and his colleagues wrote in their 2022 paper in Astronomy and Astrophysics, substantially lower than for similar galaxies generating giant radio sources. Many of the previously known giant radio galaxies were powered by black holes an order of magnitude more massive, several billion solar masses. Alcyoneus is powered by something that barely cracks the bottom of that range. Its radioluminosity, the total power output of the radio jets as measured from their radio emission, is similarly unexceptional. It is not among the most powerful radio sources in the sky. It is not even particularly bright for a giant radio galaxy. It is, in radio terms, quiet, and yet it has produced the largest structure of galactic origin ever observed. This is the Alcyoneus paradox. The object that built the largest known structure looks like it should have built something average. It has an average black hole, an average host galaxy, average jet power. The one property that might explain its exceptional size, the density of the cosmic web environment it inhabits, which appears to be lower than that of most giant radio galaxy hosts, offering less resistance to the expanding lobes, is suggestive but not conclusive. The team noted this in their paper. They could not identify a single obvious physical explanation that accounted for the discrepancy. I find this genuinely unsettling, and I mean that in the best possible scientific sense. Because what the Alcyoneus paradox tells us is that our models of what makes a giant radio galaxy large are incomplete in a fundamental way. The size of these structures is not simply a function of the energy available to drive them. Something else, some parameter we have not yet correctly weighted, some combination of factors that our simulations have not yet reproduced, is responsible for the most extreme ends of the distribution. Alcyoneus is not a confirmation of what we know. It is a refutation of the confidently held assumption that we had identified the key variables. There is a deeper layer to this, too, because when the team went looking for what was special about Alcyoneus's environment, the specific properties of the cosmic web filament it inhabits, they found something that points toward an unsolved problem in cosmology that is far older and far larger than the question of any single radio galaxy. The problem is this: the intergalactic medium in cosmic filaments, the WIM, contains roughly half of all the ordinary matter, the baryonic matter, the protons and electrons that make up stars and planets and people in the present-day universe. This is not a marginal statement. It is the result of decades of cosmological simulations that model the distribution of matter after the Big Bang. The Millennium Simulation, the Illustris Project, the Illustris TNG simulations, all of which consistently predict that the majority of baryonic matter today is not in galaxies. It is in the gas between galaxies, in the warm, hot cosmic web, and yet we cannot see most of it. We know it should be there. The baryon budget demands it, but directly measuring the WIM across the broad filamentary structures of the cosmic web has proven extraordinarily difficult. The WIM is too diffuse, too hot for emission line detection, too cool for strong X-ray emission, and too spread out for absorption line techniques to sample more than one sight line at a time. The result is what cosmologists call the missing baryon problem. Approximately 40 to 50% of the universe's ordinary matter cannot be directly observed with current instruments. What Alcyoneus offers, and what OE had originally designed his research to investigate, is a possible solution to a piece of this problem. The shape of Alcyoneus's radio lobes, their morphology, their bending, the asymmetry between the two sides, carries information about the pressure and density of the WIM through which they have expanded. By modelling the lobes as objects in pressure equilibrium with their surroundings, the team extracted estimates of the intergalactic medium density in the filament Alcyoneus inhabits. Those estimates were, as expected, lower than most giant radio galaxy environments, consistent with the hypothesis that the low ambient density is what allowed the lobes to grow so large. But the deeper point is this: Alcyoneus's lobes are so vast and so sensitive to the properties of the surrounding medium that they function as a probe of the WIM at scales never before available. The largest thing in the universe, it turns out, may be the best ruler we have for measuring the invisible half of everything, that connection between the biggest structure any galaxy has made and the most elusive stuff in the universe is not a coincidence. It is an invitation to think about giant radio galaxies not as curiosities, not as record breakers, but as instruments, as tools placed in the cosmic web by billions of years of physics, waiting for us to learn how to read them. But before we could fully read Alcyoneus, it was superseded. In 2024, the same team, the same researcher, Martin Oe, now a postdoctoral scholar at Caltech, published a paper on the cover of Nature that announced an even larger structure, one that did not merely beat Alcyoneus' record, one that raised a question so large it spans the architecture of the entire observable universe. There is a particular kind of scientist, and they are rarer than the textbooks suggest, who finds the most important thing not by designing an experiment to find it, but by seeing clearly what the data is actually showing them, rather than what they expected it to show. This is not carelessness or randomness. It requires a kind of dual discipline, the rigour to collect and process data without contaminating it with prior assumptions, and the courage to follow the implications of what you see even when they exceed the scope of your original question. Martin Owe is, by all accounts, one of these scientists. His story is worth telling in some detail, not because scientific discoveries are made by lone heroes. They are not, and Owe is always careful to credit his collaborators, but because the through line of his work over 7 years illustrates something important about how the most significant discoveries happen. They happen slowly, iteratively, in the margins of other projects, and then all at once. Owe grew up in the Netherlands, in a country that has produced an unlikely proportion of the world's astronomers relative to its population, a tradition that extends back through Jan Oort, who identified the Oort cloud of comets in 1950, through Jacobus Kapteyn, who produced the first large-scale map of the Milky Way in the early 20th century, through Antonie van Leeuwenhoek, who in the 17th century first used a microscope to see cells and microorganisms. There is something about the Dutch scientific tradition, methodical, empirical, and comfortable with speculation that is not grounded in measurement, that recurs across these figures. OI fits it. He arrived at Leiden Observatory in 2018 with the Cosmic Web project that I described in the previous chapter. What I did not mention is how the work actually felt day to day in those early months. Building the data pipeline for the reprocessing of LOTES-S images is not a glamorous task. It is not the kind of science that makes headlines. It is debugging code at 11 o'clock at night when a calibration step is producing artifacts that shouldn't be there. It is rereading the same low-profile technical documentation for the third time, looking for the parameter you missed. It is running a pipeline overnight and coming in the next morning to find that it crashed 14 hours in and having to work out why. This is the texture of scientific discovery that documentaries almost never show. The long, unrewarding technical middle before the end. The months in which nothing happens. That would make a good story. OI later described the process of refining the pipeline as iterative and time-consuming, the kind of work where patience is not a virtue, but a professional requirement. The first hint that something extraordinary was in the data came not in a dramatic flash, but in a gradual realization. As the reprocessed images accumulated, Y and his collaborators began systematically inspecting them for candidate giant radio galaxies, the long double-lobed structures that marked the termination points of powerful jets. Most of what they found was consistent with the known population. Structures a few megaparsecs in extent, hosted by massive ellipticals, conforming well to the established picture of what giant radio galaxies looked like and how they formed. But there was one object in the constellation Lynx that kept appearing at every spatial resolution they checked, at 6 arcseconds, at 20 arcseconds, at 60 arcseconds, at 90 arcseconds. Each time the two lobes were unmistakably there, not marginal detections, not borderline cases, but clear, unmistakable radio emission on either side of a compact central source. The separation between the lobes was unusually large. When OI ran the calculation, converting the angular separation to a physical scale using the host galaxy's redshift of 0.2467, the number that came back was not plausible. He ran it again, the same number the host galaxy, SDSS J081421.68522241.0, was a perfectly ordinary elliptical galaxy. Its redshift was well measured, its stellar mass was 240 billion solar masses, its black hole mass was estimated at 390 million solar masses. Nothing about it was remarkable, and yet the lobes of its radio structure were 4.99 megaparsecs apart. At minimum, the true three-dimensional separation was almost certainly larger. The team checked every possible explanation for a false detection. Could the two radio lobes be two separate, unrelated radio sources that happened to be aligned along the line of sight? The geometry was checked and found inconsistent with chance alignment. Could the host galaxy association be wrong? The optical counterpart sat precisely where it should, centered between the two lobes. Could the redshift be in error? It was confirmed from multiple spectral lines. Could there be an artifact in the data processing? The structure appeared on 4 different resolution scales, which is the hardest kind of result to fake. Each check closed off another escape route. What they had found was real, the largest structure of galactic origin ever observed. They published in Astronomy and Astrophysics in February 2022, naming the structure Alcyoneus, and the response from the scientific community was immediate and intense. But OA was not finished. After the Alcyoneus paper, OE spent 2 more years at Leiden before moving to Caltech as a postdoctoral scholar. And at Caltech, working with the same LOFAR survey data, with the same collaborators in Leiden and Hertfordshire and Paris, with the same methodical approach to data he had refined over years, he went back to the Sky survey and continued looking. Because the discovery of Alcyoneus had raised a question that its own discovery could not answer. Was it unique? Was it a singular anomaly, a 1 in a billion configuration of circumstances that had produced something unrepeatable? Or was it the first visible example of a population that was, by its very nature, at the extreme end of a distribution that extended further than anyone had mapped? The answer, when it came, suggested it was the latter, and the structure OA found that confirmed it exceeded Alcyoneus in the same way Alcyoneus had exceeded everything before it, by a margin that required a recalibration not just of the record books, but of the models that underlay them. In September 2024, a paper by OI and colleagues appeared on the cover of Nature. It described a radio structure designated J152932.16601534.4, hosted by a galaxy in the constellation Draco, located 7.5 billion light-years from Earth, nearly twice the distance of Alcyoneus. The structure had been detected in the LOFAR 2-meter sky survey, confirmed with the giant Metro-Wave Radio Telescope in India, and its host galaxy confirmed spectroscopically with the W.M. Keck Observatory in Hawaii. Its extent 7.0 megaparsecs, 23 million light-years, the equivalent of lining up 140 Milky Way galaxies back-to-back. The team named it Porphyrion after another giant from Greek mythology, this time from the Gigantomachy, the war between giants and Olympians that Porphyrion led. And Porphyrion's discovery changed the story of Alcyoneus in a way that I think is more profound than simply one record replacing another. Because Porphyrion did not merely break the record, it showed that Alcyoneus was not an isolated anomaly. It showed that structures of this scale, structures that span a significant fraction of the distance between galaxy clusters, structures that reach across the filaments of the cosmic web itself, can form in the early universe, when the universe was only 6.3 billion years old and the cosmic web was denser and more compressed than it is today. Porphyrion exists at a redshift of 0.896. At that redshift, in that epoch, the filaments of the cosmic web were packed more tightly together, and Porphyrion's jets extended across a greater fraction of the web's architecture than any comparable structure in the nearby universe. This changes everything. It means that black hole jets, at certain moments and in certain configurations, are not merely energetic events contained within the gravitational influence of their host galaxy. They are structures that operate on the scale of the cosmic web itself. They are phenomena of cosmological significance. The total power output of Porphyrion's 2 jets combined is estimated at 10 to the power of 39 watts. To pass that number, our Sun's total power output is approximately 8 times 10 to the power of 26 watts. Porphyrion's jet power is equivalent to the combined luminosity of roughly 2.6 trillion suns, not the energy stored in its lobes over its lifetime. The instantaneous power output of the jets at the time they were active, and Porphyrion's host galaxy, a galaxy roughly 10 times more massive than the Milky Way, produced this structure not through a jet mode black hole, the type associated with low-level, persistent jet activity. It produced it through what astronomers call a radiative mode black hole, the type associated with quasars, with the vigorously accreting black holes of the young active universe. This was unexpected. Radiative mode AGN were not thought capable of sustaining the stable long-duration jet activity required to inflate megaparsec-scale radio lobes. Porphyrion demonstrated otherwise. Martin Hardcastle of the University of Hertfordshire, second author of the paper and one of the world's leading experts on radio galaxy physics, offered the most plausible current explanation. The jets of Porphyrion must have been sustained for approximately 1 billion years, with remarkable stability, the jet direction remaining fixed to within a tiny fraction of a degree over that entire span. This is the duration of 1 billion orbits of the Earth around the Sun. It is a span of time longer than the entire existence of multicellular animal life on Earth. For 1 billion years, a black hole at the centre of a galaxy 7, 5 billion light-years away, kept firing, kept pointing in the same direction, kept pushing its plasma into intergalactic space, until the lobes had grown to cover 23 million light-years. I will confess that when I first encountered this number, 1 billion years of stable jet activity, I had to stop reading and simply sit with it, not because it is the most extreme quantity in cosmology, it is not, but because it translates, in a way that mass and luminosity do not, into something that human experience can almost reach. 1 billion years, long enough that the continents of Earth would have rearranged themselves beyond recognition. Long enough that the stars visible in tonight's sky would have moved to entirely new positions. Long enough that the ancestors of every species alive on Earth today were not yet what they would become. And through all of that time, the black hole fired, without interruption, without deviation, as if it were the most natural thing in the universe. Why? That question remains open. There is a temptation when confronted with objects of this scale to treat them as passive spectacles, record breakers, category defiers, things to be admired and then filed away. A galaxy this big, a jet this long, extraordinary numbers. Move on. That would be a profound mistake, because the scientific stakes attached to Alcyoneus, Porphyrion, and the broader population of giant radio galaxies uncovered by LOFAR are not aesthetic, they are functional. These structures are not merely large. They are large in a way that means they are doing things, changing things, at scales that directly affect the history and future of the universe and possibly of life within it. Let me take these consequences one at a time, from the local to the cosmological. The first consequence is one I have already introduced. These jets are instruments for measuring the missing baryons, the 40 to 50% of ordinary matter that cosmological models predict exists in the warm-hot intergalactic medium of cosmic filaments, but that direct observation has been able to account for only incompletely. The problem of the missing baryons is not trivial. It represents a gap in our accounting of the universe's contents that has persisted since the 1990s, when the discrepancy between the baryon density predicted by Big Bang nucleosynthesis and the baryon density observed in the local universe first became quantitatively precise enough to be embarrassing. The matter is somewhere. The models say it must be in the M. But measuring a medium with densities in the range of 10 to the power of -7 to 10 to the power of -4 protons per cubic centimetre, spread over scales of hundreds of millions of light years, requires either a truly exceptional background light source to measure absorption against, or a probe embedded in the medium itself. Giant radio galaxies of the Alcyoneus class offer the latter option. Their lobes are in pressure equilibrium with the surrounding WIM. Their morphology carries the imprint of the medium's density and temperature. By modelling the lobes carefully and comparing the model predictions to the observed shapes, pressures and spectral properties, astronomers can extract estimates of the WIM density in the cosmic filament the radio galaxy inhabits. This is, to my mind, one of the most elegant scientific opportunities of the coming decade. Not because it is simple, It is not, and the systematic uncertainties in the lobe pressure modelling are substantial. But because it turns a structure we cannot directly measure into a readable record of a quantity we desperately need to know, the second consequence is about energy. The jets of giant radio galaxies do not merely fill their radio lobes with plasma and then stop. As the lobes inflate, they push against the surrounding intergalactic medium, compressing it, heating it, driving shockwaves through it. This process, called radio mode AGN feedback, or JFBAC, is understood to be one of the principal mechanisms by which black holes regulate the growth of their host galaxies and the surrounding large-scale structure. A galaxy cluster in which the central black hole is active and driving large jets will have a substantially different distribution of gas density and temperature than one in which the black hole is quiescent. The jets heat the gas, preventing it from cooling and forming new stars, effectively placing a ceiling on the stellar mass of the galaxy. This is now a standard ingredient of the best cosmological simulations. Without AGN feedback in the models, simulated galaxies grow far too massive. They keep accreting and forming stars without limit, producing galaxies far larger and more luminous than anything we observe. With AGN feedback calibrated correctly, the simulation produces a population of galaxies that matches the observed universe. The feedback is real. The jets are doing the work. What the discovery of Porphyrion-scale jets changes is the radius of influence. If black hole jets can extend across 23 million light-years, if they can reach from one filament node to the next, spanning a significant fraction of the cosmic web's architecture, then their heating effect is not limited to the immediate environment of the host galaxy, or even the host galaxy cluster. It spreads across the web itself. The energy deposited by a Porphyrion-class jet event is distributed across a volume of space that contains multiple galaxy groups and filaments. The galaxies within the affected volume have their star formation rates reduced, not by their own black holes, but by the black hole of a neighbour dozens of millions of light-years away. This is a significant revision of the standard picture of galaxy coevolution. The standard picture holds that galaxies and their central black holes interact primarily through local feedback loops. The black hole regulates the galaxy fuels the black hole, and the system self-regulates over billions of years. Porphyrion implies that the feedback can be non-local, that a single, extraordinarily large jet event can leave an energetic imprint across a region of the universe large enough to encompass dozens of separate galaxy groups. OA himself, in the Caltech press release accompanying the Porphyrion paper, framed the implication directly. If distant jets like these can reach the scale of the cosmic web, then every place in the universe may have been affected by black hole activity at some point in cosmic time. Every place. That phrase deserves to sit with us for a moment. The third consequence is the one that I find most profound, and the one that connects the most directly to the world you inhabit right now. It concerns magnetism. Earth has a magnetic field. You know this. Compasses work because of it. Birds navigate by it. But the Earth's magnetic field also does something far more important than pointing north. It deflects the solar wind, the stream of charged particles constantly emitted by the sun, away from the upper atmosphere. Without that deflection, the solar wind would strip the atmosphere away over geological timescales, bombard the surface with ultraviolet and energetic particle radiation, and make the existence of complex life as we know it essentially impossible. Mars lost most of its atmosphere billions of years ago, and its core cooled and its magnetic field collapsed. The Earth kept its field, kept its atmosphere, and kept its life. Now, where did Earth's magnetic field come from? The short answer is the geodynamo, the convective circulation of molten iron in the Earth's outer core, driven by the temperature difference between the inner core and the mantle, generates electric currents that sustain the magnetic field. But this raises a deeper question. Where did the iron come from? It came, as all heavy elements do, from the deaths of previous generations of stars, from supernovae that seeded the interstellar medium with iron, cobalt, nickel, and the other heavy elements that eventually accreted into the solar nebula. But there is another ingredient necessary for the Earth's magnetic field to work: a seed magnetic field. The geodynamo is a self-sustaining amplifier of magnetic field. Once it is running, it sustains and amplifies the field through the action of the convective flows. But to start, it needs a seed, an initial weak magnetic field to amplify. Where did that seed field come from? The answer, at the current frontier of theoretical astrophysics, is the intergalactic medium. Simulations and observations agree that cosmic magnetic fields, the weak diffuse magnetic fields that permeate galaxies, galaxy clusters, and the cosmic web, must have been seeded at some point in cosmic history and then amplified by a variety of processes as structure formed. The leading candidates for the original source of cosmic magnetic fields include processes in the very early universe, magnetogenesis during inflation or phase transitions, and astrophysical processes including prominently the relativistic jets of AGN. The jets of giant radio galaxies carry magnetic field with them. As the jets propagate through the intergalactic medium and their lobes expand, they inject magnetized plasma into the cosmic web, seeding the surrounding medium with magnetic field lines that then get processed, tangled, and amplified by subsequent structure formation. Whether the magnetism we see in the cosmic web today originated primarily in the early universe or primarily in AGN jets is a question that has not been answered. But it is a question that the discovery of Porphyrion-scale jets makes dramatically more urgent, because if jets of the scale of Porphyrion existed in the early universe, and the discovery of Porphyrion at a redshift of 0, 896 tells us that they did, then their influence on the magnetization of the cosmic web could have been substantially larger than previously modelled. A jet that spans 7 megaparsecs in an epoch, when the cosmic web was denser, would have deposited its magnetized plasma across a proportionally larger fraction of the web's volume than a comparable jet would today. The early universe was a time of intense jet activity, with the highest densities of quasars and radio galaxies occurring at redshifts between 1 and 3. If a significant fraction of those early jets reached Porphyrion-class scales, and the LOFAR survey suggests that large jets may have been far more common than previously assumed, then the volume of the cosmic web magnetized by jet activity could be large enough to account for a significant fraction of the observed magnetic field in the web today. And if the cosmic web's magnetic field was seeded and spread by giant jets, then the interstellar medium of the Milky Way received some of that magnetic field as it accreted from the web during the galaxy's formation, and some fraction of that interstellar magnetic field found its way into the molecular cloud from which the solar system formed, and some fraction of that became, through a long chain of physical processes, the seed field that the geodynamo has been amplifying for the last 3.5 billion years, and some fraction of that is the field that deflects the solar wind above your head right now, that makes compasses point north, that allows complex life to exist on the surface of a small rocky planet orbiting an unremarkable star in the outer suburbs of the Milky Way. Oh, in the Caltech press release, put it this way: the magnetism on our planet allows life to thrive, so we want to understand how it came to be. We know magnetism pervades the cosmic web, then makes its way into galaxies and stars, and eventually to planets. But the question is, where does it start? Have these giant jets spread magnetism through the cosmos? It is at this point an open question. The evidence is suggestive but not conclusive. The chain from Porphyrion's jets to Earth's magnetosphere passes through too many intermediate steps and too many physical processes to trace directly. But the question is not idle speculation. It is a hypothesis with testable predictions, and the LOFAR survey data that produced Alcyoneus and Porphyrion is the kind of data that could, in principle, test it. I said at the start of this episode that what you were about to hear would not leave you the way it found you. This is the moment I had in mind, because if the hypothesis is even partially correct, then the largest structures in the universe are not separate from the smallest details of your life. The plasma jets of a black hole 7.5 billion light-years away, fired 7.5 billion years ago, may have threaded the space between galaxies with the magnetic field that eventually allowed life to persist on a planet that would not exist for another 2 billion years. The universe is not a collection of separate objects at separate scales. It is a single system, connected from the scale of a proton to the scale of the cosmic web, operating through the same 4 fundamental forces, writing its history in light and radio waves and magnetic fields across every dimension of space and time. The largest thing any galaxy has ever made is not separate from the smallest things we care about. It is part of the same story. But there is a complication, as there always is in good science, and it requires us to revisit the record books with more rigour than the headlines have applied. We have spent several chapters discussing the largest galaxy ever discovered. I have used that phrase deliberately, and I have let it stand without qualification for narrative reasons. But I owe you a more careful examination of what it means, because the question of what qualifies as the largest galaxy turns out to be one of the more productive scientific arguments of the past decade, an argument whose resolution matters not because it changes any of the physical facts, but because it changes what questions we think to ask. The fundamental difficulty is this: the radio lobes of a giant radio galaxy are not the galaxy. The galaxy is the host, the stellar system, the dark matter halo, the interstellar medium bound by the galaxy's gravitational potential. In the case of Alcyoneus, the host galaxy has an isophotal diameter of approximately 242,700 light-years. That is a large galaxy, about twice the diameter of the Milky Way, but it is not record-breaking. IC 1101, with its isophotal diameter of somewhere between 123,000 and 169 0 light-years, and its enormous diffuse stellar halo, is substantially larger as a stellar system in the conventional sense. The radio lobes are ejecta. They are material that the galaxy's central black hole has fired outward, at nearly the speed of light, into the intergalactic medium beyond the galaxy's gravitational influence. They are not orbiting the host galaxy. They are not bound to it gravitationally. They are not part of its stellar structure or its interstellar medium. In a strictly formal sense, calling Alcyoneus the largest galaxy, on the basis of its radio lobe extent, is like calling a cannon the largest weapon based on the distance its shell travels, rather than the size of the cannon itself. This distinction matters, and astronomers have been careful to make it. The discovery paper for Alcyoneus described it as the largest known structure of galactic origin, a precise phrase that acknowledges the radio lobes as produced by the galaxy without claiming they are part of it. Porphyrion's discoverers went further, explicitly describing Porphyrion as a black hole jet system rather than a giant radio galaxy, partly to avoid the confusion between the size of the jet structure and the size of the host galaxy. So, what is the largest galaxy if not Alcyoneus or Porphyrion? The answer depends, frustratingly, on how you measure. There are at least 3 distinct measurement conventions in use in the astronomical literature, each of which produces a different answer, and each of which is defensible. The first convention is the isophotal diameter, the extent of the galaxy's detectable starlight, down to some defined surface brightness threshold, typically 25 magnitudes per square arcsecond in the optical. By this measure, IC 1101 is typically cited as one of the largest known galaxies, with an isophotal diameter of roughly 123,000 to 169,000 light-years depending on the measurement. However, a careful Reddit analysis posted by a user with extensive knowledge of the NASA Pi extragalactic database noted that IC 1101's diameter, as listed in ED, is 91.58 kiloparsecs, approximately 800 light-years, while the host galaxy of Alcyoneus is listed at 74.41 kiloparsecs, or approximately 242,700 light-years. By this specific measure, IC 1101 remains somewhat larger as a stellar system. The second convention is the half-light radius, the radius within which half of the galaxy's total luminosity is contained. This is a more physically motivated measure in some respects, since it captures the scale of the central stellar mass distribution rather than the extent of the outermost, faintest halo. IC 1101 is not particularly exceptional by this measure. Its half-light radius is comparable to other massive ellipticals, and the record by this metric is held by different objects depending on the wavelength and the survey. The third convention, the one that produces the most dramatic numbers, is the total halo extent, measured out to extremely faint surface brightness limits using the most sensitive instruments available, CD galaxies like IC 1101, which sit at the gravitational bottom of galaxy clusters and have accreted countless smaller galaxies over billions of years, develop enormous diffuse stellar halos that extend far beyond what optical surveys can detect with conventional sensitivity. Deep imaging with instruments designed for low surface brightness work regularly reveals halos extending 2, 3, or even 5 times further than the isophotal diameter suggests. Under these conditions, IC 1101 may extend to 3 million light-years or more, a number that appears in some popular accounts, and may or may not be a valid characterization of the galaxy's bound stellar mass, depending on how you distinguish between the galaxy halo and the intracluster stellar light of the surrounding cluster. The honest answer, then, is that the title of largest galaxy is not a fixed, well-defined record like fastest runner or tallest building. It is a category whose meaning shifts with the measurement convention applied, and it can produce several different correct answers simultaneously. Alcyoneus is the host of the largest radiolobe structure. IC 1101 may be the largest galaxy by stellar extent. The Milky Way, it turns out, has a dark matter halo extending perhaps 300 zone light-years in some models, which does not make it the largest, but illustrates that the boundaries of galaxies are considerably fuzzier than popular representations suggest. None of this diminishes the significance of Alcyoneus or Porphyrion. The record they hold, the largest structure of galactic origin, the largest structure any individual galaxy has ever produced, is unambiguous, even if the casual shorthand of the largest galaxy elides some important distinctions. And the significance of that record is not about the number itself. It is about what the number tells us about the physics of jet formation, about the properties of the intergalactic medium, and about the influence of AGN feedback on cosmic scales. But there is a further complication that I think is worth sitting with, because it turns out that even Porphyrion may not be the ultimate record holder. In the same year that the Porphyrion paper appeared in Nature, 2024, a separate analysis of the LOFAR survey catalogue by Raphael Mostert and colleagues, published in Astronomy and Astrophysics, identified a radio galaxy designated TXS 033252 with an estimated extent of 8 megaparsecs, approximately 26 million light-years. This object has not, as of 2025, received the same level of detailed characterization that Alcyoneus and Porphyrion have. Its physical extent is based on machine learning-assisted measurements of the survey data, and the systematic uncertainties in those measurements are larger than the uncertainties in the hand-examined structures. Whether TXS 033 plus 252 truly exceeds Porphyrion will depend on follow-up observations at multiple frequencies, spectroscopic confirmation of the host galaxy redshift, and careful modelling of the lobe structure. The record, in other words, may already have been broken. We may already be looking at the second largest structure of galactic origin, while the largest waits in the archive for someone with the time to examine it carefully. This is the nature of science at the frontier. The record books are always provisional. They are the current best reading of the evidence, not a final statement about the universe. And the universe, as the last few chapters should have demonstrated, tends to exceed our best readings. There is also, lurking beneath all of these specific records and measurements, a deeper question about the population of giant radio galaxies that the LOFAR survey has now placed in sharp relief. We now know that giant radio galaxy jet systems number in the tens of thousands across the northern sky alone, a population 20 to 30 times larger than the pre-LOFAR census suggested. The survey covers approximately 15% of the full sky. Extrapolating to the whole sky, the total number of resolvable giant radio galaxy jet systems in the observable universe is likely in the millions, and the total number that existed across cosmic time, including all the systems that have long since faded below detectability, their radio lobes having cooled and dispersed over hundreds of millions of years, is vastly larger, as Oe himself said after the Porphyrion announcement. We may be looking at the tip of the iceberg. If even a small fraction of those jet systems reached Porphyrion scale or beyond, then the cosmic web has been threaded, heated and magnetized by AGN jet activity to a far greater degree than any pre-LOFAR model assumed. The implications for cosmological simulations, for galaxy formation models, for the missing baryons problem, and for the origin of cosmic magnetism are not marginal, they are structural. The discovery of the largest galaxy-produced structure in the universe is not the end of a problem. It is the identification of a gap in our understanding that the community has only recently developed the tools to begin filling. And there are three questions in particular that the current evidence cannot answer, which I want to name clearly before we move to the final chapter, because naming them is the closest we can currently get to the truth. The first: why do some black holes sustain stable jet activity for 1 billion years, while nearly identical black holes produce no jets at all? This is what Hardcastle described as requiring an unusually long-lived and stable accretion event, a configuration of the accretion disk and the surrounding medium that allows the jets to remain locked in direction and power output for cosmic durations. We do not know what determines whether a given black hole will enter this configuration. We cannot predict it from first principles. We can only observe it after the fact, in the shapes of the radio lobes it has produced. The second: is the low-density cosmic web environment the primary explanation for Alcyoneus' exceptional size? And if so, what determines the local density of the web at the location of any given radio galaxy? This is a question about structure formation, about the statistical properties of the cosmic web, about how voids and filaments and their densities are distributed across the universe. It is in principle tractable with a combination of radio surveys and galaxy redshift surveys, but it requires data at scales that are only now becoming available. The third: have Porphyrion-class jets already spread magnetism through a volume of the cosmic web large enough to account for the observed magnetic field in the local universe? This is the most consequential question and the most difficult to answer, because it requires knowing not just the current population of large jet systems, but the historical population, the jets that fired in the first 3 to 5 billion years of the universe's existence, when AGN activity was at its height, and have since faded beyond detectability. Reconstructing that population from the remnants and from the statistical properties of the surviving systems is a program of work that is only in its earliest stages. All three questions have the same structure. We've found the evidence of something enormous, and the enormous thing has left traces everywhere, but the traces are too faint and too diffuse for current instruments to read clearly. The next generation of instruments, the Square Kilometre Array, the Vera C. Rubin Observatory, future high-resolution X-ray observatories, will begin to address these questions with the kind of data that can distinguish between hypotheses rather than merely suggest them. Until then, we are in the position that science often occupies at the frontier, knowing what the questions are, knowing roughly where the answers must live, and lacking the tools to reach them. It is an uncomfortable position, and it is precisely the right position for science to be in. If we already knew the answers, we would not need the instruments. The discomfort of not knowing is the engine that drives the building of new telescopes. In the year 2026, the Square Kilometre Array, SKA, is in its construction phase, with its first observational capabilities expected within the decade. When it reaches full operation, the SKA will be, by any measure, the most sensitive radio telescope ever built. A distributed array of thousands of dish antennas and hundreds of thousands of dipole antennas, spread across sites in South Africa and Australia, connected by fiber optic cables to processing facilities capable of handling data rates that exceed the current entire global internet traffic. Its sensitivity at low radio frequencies will exceed LOFAR's by at least an order of magnitude, and its survey speed, the rate at which it can map the sky to a given depth, will be orders of magnitude greater still. What the SKA will find when it turns its ears to the frequencies where giant radio galaxies glow is not predictable with precision. That is the nature of next-generation instruments, but the trajectory of discovery, from the handful of giant radio galaxies known before LOFAR to the tens of thousands found by LOFAR, suggests that the SKA will reveal a population larger still, reaching to fainter surface brightnesses, greater distances, and more extreme sizes than the current generation of surveys can access. There may be jet systems at redshifts of 2 or 3, in the epoch when AGN activity was at its cosmic peak, that rival or exceed Porphyrion in physical extent. In the denser cosmos of that era, a jet with the same intrinsic power as Porphyrion would have met more resistance and grown less. But a jet sustained for longer, or powered by a more massive black hole, could conceivably have reached still larger scales. There is also the question of what the SKA will tell us about the morphology and polarization of jet structures at these scales. Radio polarization carries information about the magnetic field geometry in the plasma lobes and in the surrounding medium, the direction and coherence of the field lines, the degree to which the plasma is ordered or turbulent. By mapping the polarization of Porphyrion-class structures at high angular resolution, astronomers can begin to reconstruct the three-dimensional magnetic field structure of the cosmic web at the locations these jets have traversed. That is direct observational access to the magnetic history of the universe. It is one of the most technically demanding and scientifically significant programs that the SKA will enable. Meanwhile, the James Webb Space Telescope, launched in December 2021 and now in full science operation, is expanding our knowledge of the high redshift universe in ways that complement the radio surveys. JWST has already detected galaxy groups and protoclusters at redshifts between 3 and 8, in the first billion to 2 billion years of the universe's history, at densities and scales that are forcing revisions to models of early structure formation. Some of those early structures contain galaxies with active supermassive black holes. Whether any of those early AGN produced Porphyrion-class jet systems, and if so, what effect those jets had on the formation of the galaxies around them, is a question that the combination of JWST optical and near-infrared data with SKA radio data will begin to answer in the 2030s. The Dark Energy Spectroscopic Instrument, DESI, at Kitt Peak National Observatory in Arizona, which provided the redshift data that confirmed Porphyrion's distance, is in the middle of a 5-year program to measure the spectroscopic redshifts of approximately 50 million galaxies across the visible universe. The result will be the most detailed 3-dimensional map of the cosmic web ever produced. Combined with the LOFAR radio survey and the upcoming Vera Rubin Observatory Legacy Survey of Space and Time, which will image the entire southern sky every few nights in 6 optical bands, producing a 10-year movie of the variable universe. This map will allow researchers to precisely cross-reference the positions of giant radio galaxies with the local properties of the cosmic web. For the first time, it will be possible to statistically quantify the relationship between the environments of giant radio galaxies and their physical sizes, to test rigorously the hypothesis that Alcyoneus' exceptional size is due to the low density of the filament it inhabits. These are not distant speculations. These are funded operational or near-operational projects with specific science goals, specific timelines, and specific capabilities. The questions raised by Alcyoneus and Porphyrion will be addressed with real data within the lifetimes of the people currently working on them. The graduate students entering astrophysics PhD programs today are the people who will write the papers that close, or open further, the questions we have been exploring in this episode. There is one more consequence of the LOFAR survey that I want to address before the closing. because it changes the context in which all of these individual discoveries should be understood. I mentioned earlier that the LOFAR 2-meter sky survey has found more than 10,000 giant radio galaxy jet systems in approximately 15% of the northern sky, and that this represents a population 20 to 30 times larger than previous surveys had suggested. The implication that the full sky might contain something in the range of 60,000 to 70 00 identifiable giant radio galaxy systems is already a significant revision to the census of large-scale structures. But the identifiable systems are not the whole population. LOFAR is detecting the systems whose lobes are still bright enough to show up in the survey, the systems whose jets fired and faded hundreds of millions of years ago, whose lobes have cooled, dispersed into the intergalactic medium, and diluted below the surface brightness threshold, are not in the catalogue. They are gone from the radio sky. But their energy is not gone. It has been deposited in the intergalactic medium in the form of heat and cosmic rays and magnetic field. The cumulative effect of tens of millions of giant radio galaxy jet systems firing over the 8 billion years of cosmic history is a contribution to the state of the universe's intergalactic medium that no pre-LOFAR model had correctly quantified. The universe we thought we understood, the universe mapped by optical telescopes, by X-ray observatories, by the cosmic microwave background, was the universe of light we could see. The universe that LOFAR is revealing is a universe shaped, heated, magnetized, and structurally modified by the accumulated output of billions of black hole jet eruptions over cosmic time. It is a universe in which the largest structures have been continuously sculpted by the most compact objects, in which the galaxy scale and the megaparsec scale and the cosmic web scale are not separate domains but parts of a single, connected, dynamically active system. Alcyoneus and Porphyrion are the visible peaks of this system. They are the records we can read because they are still glowing. The rest of the history is written in the structure of a medium we are only beginning to learn to see. There is a quiet moment that I keep returning to in the story of how Alcyoneus was found. Martin Owe in the nature reserve in Drenthi, at the heart of the LOFAR array, looking at a reprocessed radio image that showed something he had not been looking for: 2 lobes of ancient plasma that had taken 3.5 billion years to reach his receiver, emitted by a process that began before the Earth existed, preserved in the static of the radio sky, the way a photograph is preserved in silver halide on paper. He did not plan to find the largest structure in the universe. He was looking for the cosmic web. He found something that was in the cosmic web, of the cosmic web, and, if the magnetic field hypothesis holds, a maker of the conditions that make the cosmic web what it is today. This is how discovery works most of the time, not as the execution of a plan, but as the unexpected consequence of careful attention. Not as the finding of what you set out to find, but as the recognition of something else, something that was always there, waiting for an instrument sensitive enough to see it and a mind patient enough to look. The universe rewards patience in a way that is almost uncanny. The LOFAR array, thousands of dipole antennas in the mud of the Dutch countryside, connected by fibre optic cable, listening at frequencies too low to carry music but just right for the ancient radio emissions of dying plasma lobes, is one of the more improbable scientific instruments in human history. It was built on a budget that would barely fund a modest government infrastructure project. It has no moving parts, no dish, no obvious drama. It just listens, day and night, at frequencies that no previous instrument could hear clearly, and it finds things. What it has found is a population of structures that require us to revise our understanding of how the universe evolved and why it looks the way it does. It has found evidence that the largest phenomena in the universe, phenomena operating at the scale of the cosmic web itself, are the product of some of the smallest and most compact objects, black holes, objects smaller than a solar system, operating at the centres of galaxies that are, by cosmic standards, unremarkable. The contrast between the scale of the cause and the scale of the effect is one of the most profound things about these discoveries. A black hole that could comfortably fit within the orbit of Pluto has produced a structure 23 million light-years across. The universe's most extreme large-scale structures are the footprints of objects you could not resolve with the naked eye at a distance of a light-year. This is, I think, something more than a scientific finding. It is a statement about the architecture of causality in the physical world. The universe does not distribute its effects in proportion to the size of its causes. It amplifies, it propagates. It takes the energy concentrated in the most extreme objects and spreads it across volumes so vast that the original source becomes a point at the centre, a single pixel in a radio image, dwarfed by the structures it created. The marble, to return to the analogy from the Leiden press release, does not merely roll across the floor, it reshapes the room, and we are inside the room. Every atom of iron in the Earth's core, every magnetic field line threading the geodynamo, every deflected solar wind particle that failed to strip away the atmosphere, the entire physical history of habitability on this planet is downstream of processes that operated at scales from the subatomic to the megaparsec, from the quantum mechanics of pair production near a spinning black hole to the magnetohydrodynamics of a relativistic jet, to the pressure equilibrium of a plasma lobe 16 million light-years across, to the gradual magnetization of a cosmic filament, to the enrichment of a molecular cloud, to the accretion of a solar nebula, to the solidification of an iron core, to the ignition of a geodynamo. The chain runs through 7 orders of magnitude in space and 10 orders of magnitude in time, without breaking, connecting the most violent events in the universe to the gentle compass needle pointing north in your hand. This is not mysticism. It is physics, but physics, understood fully, has a way of producing in the careful observer something very close to the feeling that mystics have always been trying to describe. The sense that the world is larger, older, and more intimately connected than the categories of daily life allow. That the distance between the largest thing and the smallest is not a gap but a thread. That the universe is not a collection of separate phenomena but a single story, told at every scale simultaneously. Alcyoneus, Porphyrion, named after giants who fought for dominion over the cosmos and did not win. In the mythology, the giants were defeated by the Olympians. But the giants these names were borrowed for were not defeated. They are still expanding. Their lobes are still pushing outward, compressing the intergalactic medium ahead of them, heating the cosmic web, threading the universe with magnetic field. They will keep expanding, fainter and fainter, for hundreds of millions of years after the last radio telescope has gone dark. We found them at the moment we could, not sooner. The instrument had to exist before the discovery could happen, and the instrument took 13.8 billion years to arrive. So, for that matter, did the people who built it. There are things we do not know yet, that the next generation of instruments will find. There are structures in the sky right now that exceed Porphyrion, hiding at the limit of current sensitivity, waiting for the SKA to listen at the frequency and depth where their ancient plasma still emits. The record we have is provisional. The record we will have is unimaginable. But here is what we do know. The universe is not static. It is not cold and indifferent, populated by objects that simply exist without interaction or consequence. It is an engine. It has been firing since the first second, and it will keep firing long after the last star has cooled. The largest things it makes are not accidental. They are the natural consequence of laws operating over time at scales that dwarf every human category, every country, every civilization, every species, every geological era. We are, in the cosmic accounting, very small. But we are also the part of the universe that turned its radio ears toward the sky and heard the oldest plasma still glowing in the dark. We are the part that named what it found after giants. We are the part that asked, and keeps asking, and will ask again tomorrow with better instruments and harder questions, and the same irreducible human need to understand where we came from and what we are part of. The universe made the giants made the fields made the planets made the life, and the life, finally, after 13.8 billion years, made the antenna. The question is not finished, it has barely begun.